Continuing our series in differentials, finally, 3 dimensions. We'll assume you've seen the first 2 and use that information. As always, this is how we do it, one variable at a time. So we're looking at parametric curves. Those curves will give us vectors. Here's a little cheat sheet for you. This is the TLDR. Go ahead and pause the video, copy all this down, laminate it, treasure it always. First thing we have to do is figure out how to compute a volume from vectors. So we have our point in space, and we'll have 3 vectors sticking off of it. So we all know volume is base times height, but this figure we're making is not a rectangle. It's got a parallelogram base, but the height's slanted, not straight, not a right angle height. That's no problem, because think of it like a deck of cards. Each card is the area of the base, and I've stacked them all up, but sliding off to the side. I just slide all those cards back, and my volume is base times height. Labeling my vectors, A and B, then the area is the length of their cross product. To get our height, we'll look at our slant vector, our vector C, and our cross product vector is in the direction we want. It's the perpendicular direction. So the height is the dot product with C against the A cross B direction. The direction vector, of course, is the unit vector, so just the vector divided by its length. Volume, height times the area of the base. Swap in our height in terms of vectors. Swap in our area of the base in terms of the vectors. And the length of the cross product vector cancels out. This is called the vector triple product, if you want to look it up somewhere. We had to compute the cross product first, and then dot C against it, so I'll put parentheses around it just to remind ourselves we need to do that first. Since we're looking at a volume in 3 space, there's no equation for it. I want all 3 parameters. Volume, 3 parameter object. There's multiple parameterizations you can use. In this course, we'll just stick with the 3. The default, the cylindrical, the spherical. First up is the default coordinate system, the easy one. So we're going to use the coordinates as parameters. So our parameters are x, y, and z. Vary x, fixing y and z, get a curve out of the point. Vary y, fixing x and z, get a curve. Varying z, fixing x and y, a vertical line. For our parametric description, the coordinate of the point and the standard coordinates on the left. On the right, the parameters that describe it. For the standard coordinate, it's the same, of course. Now, look at the tangent vectors to those curves. The easy way to get that is to rewrite the parametric description in vector form and then take my partial derivatives. Partial derivative in x, the partial derivative in y, the partial derivative in z. The volume differential is the vector triple product, absolute value. Here it's the same symbol as length of a vector. It always means size. Z partial is k, x and y partial is I and j crossed gives you k, and k dot k is 1. And so here we go. dv is dx, dy, dz. Next up, polar coordinates. So we have our point in space, but this time we're going to access it using our r and theta variables. So our radial axis spun over by theta. Going through the point, r varies, theta and z are fixed, giving us a radial line. Theta varies. That's a circular arc in the plane, but it's parameterizing that point, so it's a circular arc on that point. R is fixed, Z is fixed. And then our last coordinate line, Z varies, R and theta are fixed. Getting our parametric form, X, Y, Z on the left, that's the parameters we use to describe it on the right. Polar coordinates are cosine theta, our sine theta, and z. Write it in vector form, and we can take our tangent vectors. Our tangent vectors are our derivatives, partial on r, partial in theta, the partial in z. So our point in space has three vectors sticking off it. Our tangent vector in the radial direction, our tangent vector in the theta direction, and our tangent vector in the z direction, all scaled by the differential. My volume differential is the vector triple product of the three tangent vectors. The radial and theta direction vectors we did last video, that was r scaling the k vector, the z partial is the k vector, dot them together, that's r. And our volume differential, r dz dr d theta. On to spherical coordinates. We use the radial axis to help visualize, but we don't use that variable. We use theta, the rotation. We're at the point x, y, z, so the curve that goes through the point. With that theta, we vary that theta, we hold rho and phi fixed. Get that one parameter curve. Varying rho, the radius. Get our radial line from the origin. And varying phi, the drop-down angle from the vertical. So we have our three one-parameter curves. This is spherical coordinates, so just to reinforce, here's my little lumpy sphere. So at every fixed radius, thetas and phis map out a sphere. So we have our point on the sphere, thetas are latitude lines, and phis are longitude lines. And then rho is the radius of the sphere. Varying rho gives us our radial line. Parameterizing, our point x, y, z is its coordinate in the standard coordinate system. And we're going to convert from spherical to standard. R is rho sine phi. So in the polar description, r is replaced by rho sine phi. Z is replaced by rho cosine phi. So in doing this, remember I'm using the triangle. So the point is r units on over, it's z units up, rho units out, and phi is our drop-down angle. So the triangle that relates the variables, my rho, phi, z, r. Z is cosine, r is sine. Rewriting in vector form. taking our partial derivatives, partial derivative in rho, partial derivative in theta, cosine goes to minus sign, no thetas in the third component, and our partial derivative in phi. Looking at our tangent vectors now coming off of our point, we have our radial tangent vector. So the theta tangent vector is parallel to the xy plane, and the phi tangent vector is in the zr plane with the rho tangent vector. So when we do our triple product, it's going to be easier to dot the theta vector with the cross product of the rho phi vector, because those vectors will be parallel and they have a 0k component. So it might be just a little less work. Of course, it doesn't matter. Factoring out our differentials. Now for the computation. So we'll do our cross product, the I component, subtract the j component, and the k component. And as expected in the k component, the terms are the same and they cancel out, so it's parallel to the r theta vector. Factoring out the rho sine theta, a sine squared plus cosine squared turns into a 1. Factoring out the rho cosine theta, sine squared plus cosine squared is a 1. And we get our cross product vector. Dot it with the theta tangent vector, rho squared sine phi is common, factor it out, leaving behind a sine squared plus cosine squared, which is a 1. So we get our volume differential, rho squared sine phi, d rho, d phi, d theta. Quick recap of what we just did. Standard coordinate system, standard parameterization. And it was just dx, dy, dz. Using polar coordinates for my parameterization. dv was r, dz, dr, d theta. Using our spherical parameterization, dv was rho squared sine phi, d rho, d phi, d theta. And we're using the triangles to transfer between parameterizations. The polar triangle, r theta xy, the spherical triangle, rho, phi, z, and r. 3 different parameterizations for space, depending on what coordinate system you want to use. The geometry of the region usually dictates which system is best. Cylinders, cylindrical, spheres, spherical.